Okay, good evening. I will be having a long video format topic for starting tonight, and the title of the topic is Alternating Current Machines. We are now through with alternating current circuits. So we will proceed with the so-called alternating current machines. Alternating current machines, the three most important alternating current machines are the alternators or the generators, the one creating our AC voltage. The number two will be transformers, which are either single phase or three phase transformers, meaning to deliver the voltages to household clients. Okay, we need transformers. So the number two AC machine that we will be discussing here is transformers. And the third one will be, it's either a synchronous motor or induction motors. Why? Uh, for business entities, there are so many loads inside the business entities which are motors. And most of them are actually induction motors or synchronous motor. Okay, so the number three topic may be the synchronous motor or induction motor. We study the concepts and the computations that involves with the operations of alternators, transformers, and induction motor. Okay, let's proceed. This should be lesson number one. It's a little bit boring because in here, in the long video format discussion, we study concepts, okay, theories regarding the operation or construction of these AC machines, plus the computations involved. Okay, let's proceed. Alternating current machines, lesson number one. AC, alternating current machines, lesson number one. The title of the topic is Introduction. Okay. Underscore transformer. So the first topic under AC machine will be transformer. For the meantime, it is just single phase. Single phase. Okay. Because later on, upon reaching the so-called three-phase transformer, that will be a different story. So the basis of the three-phase transformer is actually the single-phase transformer. So we will discuss first the concepts and the computations involved under a single-phase transformer. But first of all, at least we know what is the physical appearance of a transformer. A transformer will be something like this. A transformer got a primary winding. Okay. This is an iron core. This one, the rectangle thing, in which the windings are wound, right? The windings that are placed on the secondary are the secondary windings. This one. So take note of the direction, because later on we will be using the current direction for us to know the direction of the magnetic flux produced by the current passing through the coil. Okay, so this is a little bit a study of physics. We will be using the so-called Lenz's law over here, and how to determine the direction of the flux produced or magnetic field produced by a current passing through a coil wound through an iron core. Okay, so this is an iron core. Iron core. Made of steel plates. Right? The side view of this, or the isometric view of this, will be something like this. It will be slices of steel plates like that. That's the isometric view. I'm just showing the frontal view, right? So this core here consists of many strips of steel plates. This should be the formation. It's a rectangle. Okay. So for a transformer, there should be a primary winding. There should be a secondary winding. There should be an iron core. And if we try to intermix these ones, that is termed to as a transformer. Okay. Transformer meaning we will transform a different voltage from a high level to a small level, or from a low level to a high level, something like that. That will be transformer. That's why the word transformer, it's synonymous to transformation. Meaning, if we apply a certain voltage here, since this is a transformer, and assuming this voltage is high, and if we wanted a small voltage at the secondary, we could do that. That's why the term 2 is transformer. We will transform that high voltage to a low voltage. That's why it is so-called transformer. Or the other way around, we could have a small voltage here, and if we try to change the number of turns on the secondary, we could make the voltage on the secondary bigger. Okay, that is also transformation. Transformation from small to bigger, or transformation from bigger to smaller. That's why the term 2 is transformer. Okay? Okay, let's try to bring out the operation. Before I will try to bring out the operation, I will be placing the notations or the, what you call these markings on the figure, right? The voltage across this will be designated by capital letter E with the subscript P, meaning primary voltage. This subscript P here refers to primary side. Okay, so E with the subscript P meaning primary voltage. The voltage across the terminal of the secondary, the two terminals. That's why my last topic under AC circuit is single phase and three phase loads. So if you are to be considered a single phase load, you should only be connected to two lines, right? So we are doing the so-called study of single phase. This is the symbol for phase. It will be something like that. So if this is one here with that symbol, meaning it is single phase, right? The voltage across the terminals and the secondary is capital letter E with the subscript S, meaning the secondary voltage. The secondary output voltage, the one that goes to the load, it is wherein we connect our utility line or our service entrance to our houses. It is this, right? Or what's next? The graph, this side here is the AC source, right? The voltage we applied here is an alternating current source, and it should be a generator, alternator, the one coming from our power plants, okay, hydro plants, nuclear plants, turbines, okay, from solar panels, okay. Like in the Philippines, we got the so-called geothermal there. We get the hot thing underneath the earth, and we made that as just like a steam, so we could generate a power from the, what you call this, outburst of steam coming out. We got that in the Philippines, geothermal power plant. So this AC source comes from many sources. It could be geothermal, nuclear, from dams, hydro, okay, from turbine plantations, okay, meaning plantations, it's lots of turbines, so it will be turbine plantations. It is still considered a power plant. So the source of this came from the so-called generator side. But for the meantime, we do not talk about it. That will be another topic, right? So the voltage applied here is coming from the generator, okay, from the utility company. This symbol here under the study of transformer, we consider this one as flux. Flux or magnetism. Because to produce an induced voltage, there should be a current. What happens now? Okay, I will try to erase the other ones so it will look nice. Okay, there should be a current I and there should be a flux. There should be a current, there should be a flux so that we could produce an induced voltage. Okay, these are the three requirements. Okay, so the current on the primary side is designated by capital letter I with the subscript B, meaning primary current. And the corresponding current on the secondary side, this is capital letter I with the subscript S, meaning secondary current. So I place it here. If the applied voltage here is alternating, this is alternating, right? Supposed to be the nature of the voltage that is coming out on the secondary will still be an alternating. It depends. If it is a step-down transformer, this is a bigger alternating current and this should be a smaller for step down. But for a step up, if this is smaller, okay, if it is a step up, the current here should be bigger. Okay, but what I mean is that if this is alternating, what comes out on the secondary side will also be alternating. Okay, it's just like if the frequency on the primary side is 60 Hertz, primary side, supposed to be the frequency on the secondary side will also be 60 Hertz. Okay, oh, that's it. I got the direction of the flux for this configuration, for this drawing, okay? The current is in this direction, the flux should be like this, and on the other side, it's the opposite, right? Okay, let's try to bring up the operation. There should be an input driving voltage. There should be. For this transformer to produce a voltage here, that will be needed by household here, okay? There should be an input voltage here coming from the generators. Without it, we could not produce. If the generator or power plant is down, we call it brownout or blackout, right? So if this is dead, there will be no voltage here, no voltage on our houses, it's brownout. That's the time we need this so-called brownout. Okay? So for us to have lighting, or we could use our generator, or what they call these motors inside our houses, there should be an input voltage for the transformers that is hanging on the post, okay? Without it, it's brown out, okay? So to produce a secondary voltage in which we are using it in our houses, there should be an input driving voltage, okay? And that input driving voltage is just like the one coming from, okay, California Edison Company, okay? Without it, it's brown out. No voltage here. Right? So the first requirement is there must be an input driving voltage. What's the next one? If there is an input driving voltage, this current here will produce a flux that will circulate on this iron core. It will circulate. If there is current here, it will circulate. There is a magnetic field that will go around here. And as the magnetic field passes through the secondary, okay, it will cut the windings, okay? It's just like a magnetism, a strong magnetism that cuts this winding here. If there is magnetism and there is winding, there should be an induced voltage here. Whether we like it or not, there should be an A sub S here, the one we are using in our home, okay? Because without this flux, okay, no voltage that will appear here. So if there is current on the primary, there should be flux circulating, and this flux is cutting this a coil over here on the secondary. So an induced voltage will come out. Okay, there should be an induced voltage over here. Okay, that's number 2. And what's number 3? Produce an induced voltage. Oh, that's the one I've been discussing. Okay. The requirement for a transformer for the operation will be, there should be an input voltage here. If there is an input voltage here, current will pass through the primary winding, okay? And a flux will be produced on the iron core or steel plates, okay? It will circulate like this. Then this flux will cut these windings on the secondary, and as it cuts, okay, there will be an induced voltage on the secondary, and that induced voltage is the one we are using in our home. Okay, that's the operation of a transformer. It's only three, right? It's only three. There should be an input voltage coming from the utility company. Without it, this is product, no voltage here. And if there is current, whether we like it or not, there should be a flux. Okay, a magnetic field that goes around. Okay, and number three, if this flux or magnetic field cut the what you call these windings that is wound on the secondary, it will produce an induced voltage ES. Okay, this is the one we are using in our houses, and the value is actually 120 volts. Okay, that's the operation of a transformer. This right-hand rule is just the procedure on how to determine the so-called direction of the current, okay, when that current passes through a coil. It is termed to as the so-called right-hand rule. I will try to read it. The right hand finger curl around the coil, okay, then the thumb points in the direction of the magnetic field down the center of the coil. Meaning to say, if this is the core, okay, and this is the coil, okay, the curling of my fingers points to the direction of the current, and the direction of the thumb points to the direction of the flux or magnetic field produced. Okay, this is the curling of the current. The curling of the finger points to the direction of the current, and the direction of the thumb, okay, points to the direction of the flux produced or magnetic field produced. It is this. Okay, for this primary side, it's like this. Okay, the current is counterclockwise. Okay, so the flux produced should be like this. It is this. On the other side, it's the reverse direction. Okay, it's like this. The current is like this. It goes with the curling of the hands. Okay, so the curling of the hands shows the direction of the current passing through the coil, and the direction of the thumb, okay, shows the direction of the flux produced or the magnetic field. That's it. That's the so-called right-hand rule. Don't forget that one. You got an iron core, okay, you curl with your hands. The direction of the curling of the hands points to the direction of the current passing through the coil, and the thumb points to the direction of the flux or magnetic field produced. Okay? This is a summary. Curled fingers, current direction. Okay? Thumb, flux direction or magnetic field direction. Okay? It's like this. The curling of the hands points to the direction of the current, and the direction of the thumb points to the direction of the magnetic flux produced. Right-hand rule. Okay? Annotations. A transformer changes the relationship between current and voltage in AC circuits. I will try to explain this one later on. This could be explained by using equations. Number two, a transformer could either step up or step down the input voltage. Meaning to say, the input voltage, if the transformer is step up, if this is 120, I could make this 240, 480, or it depends on what type of transformation I would like. That's the meaning of that one. If there is a small voltage here, I could make this voltage bigger by changing the number of turns on the secondary. I could do that. That's why it's so-called transformer, or it will transform. Right? Number three, of course, no moving parts. Right? Number four, require less care. Of course, no moving part, require less care, right? Unlike in the motor loads or alternators or generators, the generator is moving. That's why we should care for the generator, because if it breaks down, it's brown out, right? And number 5, this is regarding calculations already. The efficiency of transformers are high. Transformer efficiency is in the range 90 to 95%. Because there are no moving loads, of course, the efficiency will be high. Unlike in the induction motor or alternators, there are moving loads. They are moving, right? They are rotating. And as they rotate, the parts are worn out, right? So it depends on how severe the worn out may be. If the worn out is severe, okay, of course the efficiency will be less, right? For number 1, it says it will change the relationship between current and voltage. The transformer equations are these. The voltage, the value A, later on when we go to the calculations, I will explain this one. A will be the ratio secondary current over primary current, and this should be equal to the number of turns on the primary. So sorry for this one, it should be in S. This should be in S. Okay? Number of turns on the secondary, and this should be equal to the induced voltage on the primary. What's happening? It's EP. It's this should be ES. Getting old. Okay, I will repeat it. A under the studied transformer will be, I will explain this one later on. It will be the ratio secondary current over primary current. This should be equal to the primary number of turns over the secondary number of turns represented by N. And this should be equal to the ratio of secondary primary induced voltage over the secondary induced voltage. And from here, actually, it will be equal to AT close quantity with the subscript P. This should be AT with close quantity with the subscript S, meaning for a transformer, the ampere turns, the product of number of current times number of turns on the primary should be equal to the product of the amperes on the primary or secondary in the number of turns on the secondary. Actually, that will be this equation here. This equation is actually IS, it is this one, IPNP, it is this. Okay, forget the third one. We derive this one by equating this one here. The product of IS and S should be equal to the product of INP. That is termed to as I is current, so current is ampere turns. Ampere is current. T is number of turns. Primary, it will be the ampere turns of the secondary. The product of IS and S should be equal to the product of INP. Thus, that is the term to, we could change the relationship. Okay, the next one. The volt ampere on the primary should be equal to the volt ampere on the secondary. Volt ampere is apparent power, meaning the apparent power on the primary should be equal to the apparent power on the secondary. So, E is actually voltage, right? And I is actually current. So, the product of voltage in ampere on the primary should be equal to the product of voltage in ampere on the secondary. Actually, what we did is we consider this to here. We cover the middle one, so we took the product of ESIS and we take the product of EPIP. Okay? That is the meaning of annotation number 1. That we could change the relationship between current and voltage in AC circuit by using these two equations here. Actually, these two equations are actually used in the design of transformers. Because actually, to change the current, okay, if you want the volt ampere on the primary to be bigger, you make the number of turns bigger. Right? So, if the current on the primary is also bigger, okay, a product of a big number times a big number will be still be a big number. right? And this should be equal to the value on the secondary. You could make this one smaller or smaller, but if this is bigger and bigger, this should be bigger also, and this should be bigger, so what will come out will be still be a big number. Because the product of IP, NP, and ISNS should be the same. There is an equality sign here under algebra equality, so this is actually an equation, right? That's the meaning of annotation number 1. And regarding the voltage, we could manipulate this one. If you want the current to be big and the applied voltage to be small, we could do that. Even also on the secondary, that's the meaning of annotation number 1, that we could change the relationship between current and voltage by using these two equations here. Okay, that's it, guys. That's the introduction of the study of transformers. So the next time around, I will be presenting the equations and how to use these equations here. We will derive these ones, because in the design of the so-called load for transmission lines, we will be using these ones. Okay, good evening from Los Angeles. This is Professor David J. De Los Reyes.